Welcome, this is Basic Probability Part 2. And no matter where your probabilities come from, they could be subjective, empirical based on data, they could be relative frequency, what have you. The rules that we use to work with probability are all the same. And that's what we go over right now. The rules of Probability Club are we talk about Probability Club. The most basic rule is probabilities are always in interval 0 to 1. So if you get a negative probability, you get a probability bigger than 1, that's not legal. We also use capital letters to denote events. So we'll talk about the probability of A, the probability of B, things like that. Rule 2 is that we have all the outcomes of our sample space, they have to sum up. The probabilities of all the outcomes have to sum to 1. If it's less than 1, we're not exhaustive, we've missed an outcome. If the sum is larger than 1, we're not mutually exclusive. Two things can happen at the same time, and that's also a no-no. Rule 3 is called the complement rule. So we have an event A we call not A. The negation of A is also denoted A bar, or the complement of A. So suppose the probability you get the class on time is 0.8, the probability you do not get the class on time is 0.2. The complement rule is pretty straightforward. P of A bar equals 1 minus P of A. And you look at that and you say, do we really even need to write it down? Well, A and A bar can't happen at the same time. It's either going to rain today or it's not going to rain today. So it makes sense that P of A, where does this rule come from? P of A plus P of A bar equals 1. Because one of them has to happen. One of them has to happen. So we get the complement rule. And you look at this and you're like, why is that a useful rule? It's often easier to find the complement of an event than the event itself. And so we'll see several instances where we like to work with the complement instead of the event itself. In the birthday problem, if A is the event, no one in group shares the same birthday. The complement of that is at least 2 people share the same birthday. And it's much easier to find the probability of A. We assume birthdays are independent. So what's the probability no one in group shares the same birthday? You have a bunch of unique birthdays. So if we're looking at these 22 people or so in a room, 365, the first birthday is fixed. The second person can have any of 364. It's got to be a different birthday. The next person can have any of 363 because it has to be a different birthday. You multiply them together, and the probability that no one in the group shares the same birthday is 0.493. The complement probability would then be 1 minus that, 0.507. This is for 23 people. So again, it's sometimes a lot easier to find the complement than the probability of an event directly. And we'll talk more about that in a little bit. What we often work with in our class are what are called contingency tables. They're called joint tables. It's a table of counts. We looked at 1,000 trading days. It's about 5 years of data. GPS is Gap, AAPL is Apple. And we just cross-classified on how many days did they both rise and how many days did one decline, the other rise. How many days were they unchanged? Very unusual for a stock to remain unchanged for the day, just because these are both high-volume stocks. To start the day where they, the end of the day where they started, that's an unusual event. So this is a table of counts, and notice that we have the different outcomes this way and this way. The outcomes are mutually exclusive and exhaustive. Keep that in mind. And a table of counts not entirely that useful. We divide by the total of 1,000 days, and we get what's called a joint probability table. We sum up everything inside this table, it's going to sum to 1. What you can also do is sum across, and you can also sum down. So if you sum down, you get these numbers. You sum across, you get these numbers. And it turns out that these numbers add up to 1 also, and these numbers also add up to 1. The things inside the table are called joint probabilities. A joint probability is the probability of 2 things happening at the same time. So the probability Gap rose that day and Apple rose is 0.338. The probability that Gap declined and at the same time Apple declined, 0.293. The probability that Gap rose and Apple's unchanged, very small, 0.001. Those are called joint probabilities, often referred to as the probability of A and B. It's a joint probability, 2 things at the same time. So again, notice the ands here. Marginal probabilities are literally called marginal probabilities because they're written in the margins of the table. These are the marginal probabilities. And they're just, if you're interested in one variable, we only want to look about gap, we only want to look at gap, or we only want to look at apple, we would look at the marginal probabilities. So again, there's three tables you can look at. This thing is called the joint probability table. This is the marginal for apple, this is the marginal for gap. And notice how that adds to 1, that adds to 1, everything inside the table has to add to 1. Now, what's nice is, or you want to remember, you can always go from a joint to get the marginals. So you can always go from inside the table out. You can always go from inside the table out, you just add down or add across. You can always go from the joint to the marginals. You cannot always go from the marginals to the joint. That only happens in very specific instances, but you cannot always go from the marginals to the joints. So remember, that's not always true. In general, it is not true, actually. Some additional rules we can do. We have the addition rule. This is the probability of A or B happening. The probability of A or B happening is the probability of A happening plus the probability of B happening. And you have to subtract off the probability of A and B happening at the same time. The reason you do that is you don't want to double count. What's the probability apple rises or gap rises? It's the probability that apple rises plus the probability gap rises. In fact, if you stopped here, you'd have a problem because you'd be bigger than 1. You're double counting one cell. You subtract it off to make sure you don't double count. That's called the addition rule. And then once we have the addition rule down, we can start looking at some more advanced ideas, and we'll do this in the next video also. We'll expand on this. There's something called conditional probability. And conditional probability gives you some additional information and then asks, does the probability change, or what's the probability given some additional information? For example, suppose we want to know the probability that an 8 as a sum turns up when you roll 2 dice. Turns out there's 5 ways. I don't know if I can actually draw that. I'll try to do that here. There are 5 ways to get an 8. The probability is 5 out of 36. Now suppose you're going to roll 1 at a time instead of 2 at the same time. And you have a better chance of what's going to happen in terms of getting an 8. So if our first roll is a 1, what's the chance the sum of the 2 dice will be an 8? Well, it's going to be 0, because what do you have to roll? If the first one's a 1, you're going to roll a 7 on the second one to get an 8. You can't do that. That's a 0. If the first roll is a 3, what do you need for the second roll? You need a 5. What's the chance happening? 1 out of 6. So that's conditional probability, and it changes. Conditional probability is asked, what's the chance that A happens given that we know B happened? The package doesn't make it to Chicago by 9 a.m. tomorrow. What's the chance we lose the deal? Given we spend $10 million in research, what's the probability of inventing a successful competitor to the iPod or the iPhone or something like that? Use of the words if and given. We use the notation A bar B, and that says, given that B happened, what's the chance A also happens? These are 3 different probability statements. If a person has HIV, the probability they will test positive on the screening test is 90%. If a person tests positive on the screening test, the probability they'll have HIV is 90%. The probability that a person has HIV and tests positive is 90%. This is a conditional statement. This is a conditional statement. This is a joint statement because of the word and. If, and that's the and there. So we can talk about conditional statements. We can talk about joint statements. Conditional probability is written in this form. We say the probability of event A given event B has happened. And of course, this only makes sense if you're being technical, if that's true. You can't condition on something that doesn't happen. So you have to assume that the probability of B is bigger than 0. But this is called a conditional probability. And we often are interested, this is looking ahead a little bit, we're often interested in this P of A equal P of A given B. That's a question that we always ask is, knowing B happened, does that affect A? Is there a relationship between A and B? Does the probability of A stay the same? Does it differ? Does it get higher? Does it get lower? It's an interesting question. How does B affect A? The definition of conditional probability is pretty straightforward. We're just asking, out of all the times B happened, how often does A also happen? And we compute it this way. It's just a ratio of the joint on top, the marginal on the bottom. Out of all the times B happened, how often does A also happen? Basic idea here, just showing you some math. 70% of your friends like chocolate, 35% like chocolate and like strawberry. Given you like chocolate, what's the probability like strawberry? You're just going to take the joint probability over there, 0.35, divided by 0.7, and you get the answer. What's the probability you'll draw a king, given you've drawn a face card? Well, just by definition, the probability of king given face card is king and face card, or the probability of face card. And there are 12 face cards, that's 12 over 52. And a king and a face card, that's the probability of drawing a king. Because a king is a face card, so that's 4 out of 52. It's 1 out of 3. So straightforward, pretty much, what conditional probability is. If you want some practice with this, and we'll post the solutions to here, here's a table of counts. And we have 545 total in the table. It's going to be an important number here. What's the probability of selecting a student whose favorite sport is skiing? Well, that would simply be 171 out of 545. What's the probability of selecting a 6th grade student? That's 155 out of 545. And then what are the next two? The next two are conditional probabilities. If the student's a 7th grade student, what's the probability that the student prefers ice skating? If the student selected prefers snowboarding, what's the probability that the student is a 6th grade student? And I won't write with my finger anymore because that bothers some people. And I don't know why it bothers Julie. And I'll post the solutions to this so you have it. But again, this stuff is mechanical at this point. Should not be that difficult to figure this out. So what do you want to know so far from our basic probability 4A? What's probability? What are events? What's mutually exclusive? What's collectively exhaustive? Joint probability, marginal probability, the addition rule, and a basic intro to conditional probability. Next video, we'll cover it a lot more. Thank you. Hope you're having a great day.